Geometry students, I am going to try to make this video short, but we are doing two sections because I hope most of this is review from your life, just dealing with quadrilaterals. So a couple of things that I think are interesting. We have all these theorems now in this next section that say if both pairs of opposite sides of a quadrilateral are congruent, then that quadrilateral is a parallelogram. Last section had this same theorem in reverse, right? These are called converses. The last section had a theorem that says if something's a parallelogram, then the opposite sides are congruent. So you could think of that as if and only if, right? It goes both ways. Same thing with opposite angles congruent in a quadrilateral. If the opposite angles of a quadrilateral are congruent, then that quadrilateral is a parallelogram. The same is true with the diagonals bisecting each other. If the diagonals of a quadrilateral bisect each other, then it's a parallelogram. You could prove those four theorems. This one is really interesting. This is one we didn't have in the previous section, so I would read this one closely. If one pair of opposite sides of a quadrilateral are both congruent and parallel, then you can prove that the quadrilateral is a parallelogram. What I would do is I would introduce a diagonal here. I would be able to say that this angle here is congruent to this angle here. I could then say that this side was congruent to itself. I would have two triangles congruent by side. Oh, that's a terrible drawing there. Sorry, this angle here. Side angle side congruent to side angle side. Then I get that this angle here is congruent to this angle here, which means this side is parallel to this side by if AIA congruent, then parallel. And then I would have the quadrilateral as a parallelogram by definition. I want you to prove these other three theorems. I want you to prove this one, that if the opposite sides are congruent, then it's a parallelogram. If the opposite angles are congruent, then it's a parallelogram. I want you to prove those. I want you to prove that if the diagonals bisect each other, then it's a parallelogram. And that one's pretty easy because getting the triangles congruent. Those are your only three proofs to do tonight. Chai and Carter, do those three proofs. Eli Conley, do all three, not just two of them. Okay, next, here's a little summary. And that's one whole section. So I'm not going to spend too much time with that tomorrow in class because it's pretty straightforward. The next section, I disagree with the book definition of these three shapes. The book says a rhombus is a parallelogram of four congruent sides, a rectangle is a parallelogram with four right angles, and a square is a parallelogram with four congruent sides and four right angles. I'm going to cross out parallelogram and I'm going to say quadrilateral. I'm going to say a rhombus is a quadrilateral, four-sided shape, quadrilateral, rectangle, quadrilateral. If I use quadrilateral, I can say, well, hey, look, opposite sides of this quadrilateral are congruent, therefore it's a parallelogram. And it's more powerful to prove that a rhombus is a parallelogram than it is to define it that way. Same thing with a rectangle. Opposite angles are congruent, therefore it's a parallelogram. And if I do the same thing with a square, quadrilateral, that has four congruent sides or four right angles or four congruent angles, I might call this a regular quadrilateral, meaning equiangular and equilateral. And then again, you could prove that this is a parallelogram. There's a beautiful image in the book. I'm going to skip this and come back to it. I love this Venn diagram. It shows a rectangle, no pun, like just a coincidence, but it shows a big box holding every parallelogram in the world. There's a parallelogram, and every other parallelogram is in there. In that box of parallelograms, there's a subset called rhombuses. Oh my gosh, what a terrible book. Rhombi. Should have an I. Rhombi, not rhombuses. Terrible. So rhombi, and that's all sides are congruent. And then there's rectangles, and that's all angles are congruent, or all angles are right angles. And then where rectangles and rhombi overlap are squares. A square is a rectangle. A rectangle is not necessarily a square. A rhombus is not necessarily a square, but a square is a rhombus. A square, a rhombus, and a rectangle are all parallelograms, but parallelograms are not necessarily those three shapes. Going back to this slide here, the book quickly contradicts its own definition and does this. A quadrilateral is a rhombus if and only if it has four congruent sides. Well, why didn't you just define it that way in the first place? Same with a rectangle, same with the square. I would take out, I wouldn't call it a rhombus and a rectangle. I would say equilateral, equiangular, equiangular, equilateral. I like that language better, but same idea. Now some interesting properties of rectangles and rhombi. A rhombus, something is a rhombus if and only if its diagonals are perpendicular. So that means if you have a rhombus, you know the diagonals are perpendicular. If you have diagonals that are perpendicular, you know it's a rhombus. If you know it's a rhombus, you know it's a parallelogram. You also know that if the angles, if the angles of the quadrilateral are bisected by the diagonals. That's true if and only if it's a rhombus. So if rhombus, diagonals bisect these angles. If the diagonals bisect angles, then you can prove it's a rhombus. And then with a rectangle, you can show that the diagonals are congruent. So the diagonals bisect each other, but that's because we can prove a rectangle is a parallelogram, and the diagonals of any parallelogram bisect each other. But you can prove that the diagonals are congruent in a rectangle. So if you're keeping track at home, and I do this on the test, I can start to ask about certain properties like opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. Diagonals bisect each other. And then I can add in the properties from today. And then here I can write parallelogram. And then I can write rhombus or rhombi. And then I can write rectangle. And then I can write square. And later I'll write trapezoid, isosceles trapezoid. And I can start to build a chart. Hint, 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 this is on the next test. And then your job is to fill in whether it's true in that chart or not. Good? And if it's true for a parallelogram, it's true for a rhombus, true for a rectangle, true for a square. Good? So I would generate my own chart tonight of all the different properties we've talked about. They're all in this video. You can't go back in the slides like me, but you could rewatch the video. So here's a ton of properties of parallelograms. And then you go forward and look at the properties of a rhombus up here, and a rectangle here. And if it's a property for a rhombus, it's also true for a square. And if it's a property of a rectangle, it's also true for a square. All of these are true for squares as well. Now, you can't replace rhombus with square here because there's more to make it a square. But if it is a square, then the diagonals bisect each other. If it is a square, then the diagonals are congruent. If a quadrilateral is a square, then the diagonals are perpendicular. So those properties are true. Again, this is a super short video. I stumbled over my words again, but hopefully this is kind of grade school stuff, right? How long have you been working with shapes like quadrilaterals? So just reviewing these properties. Remember Chai and Carter to prove Theorem 8.7, Theorem 8.8, and Theorem 8.10. You do not have to prove Theorem 8.9. I proved it in the video, so you could write out the proof that I described, but I'm not going to make you do that. Please please do those 3 proofs. Good? All right, kids. Have a wonderful night. Talk to you tomorrow. Peace.